Hi everybody, today we're going to be talking about dimension of a vector space. Okay, dimension is basically another instance of this is something that we've been talking about, that we know about, but we're just giving an official name to. And before we actually talk about dimension, we need a few results first. Okay, so first, this one here, theorem 4.5.9, so the ninth theorem in chapter 4 of our book, which is in section 4.5. If a vector space V has a basis containing n vectors, then any set with more than n vectors is linearly dependent. Okay, let's remind ourselves of a few things. So a basis has to have two main properties. Now, what are those properties? I'm going to pretend like you said it out loud to your computer. You said that it was linearly independent and that it spans the vector space V. Okay, so if you have a set like that with n vectors, any set with more than n vectors is linearly dependent. This is basically just a generalization of the result that a set in Rn with more than n vectors is linearly dependent. So the basis of Rn, right, is going to be the columns of the n by n identity matrix, right? They look like this. So that's a standard basis for Rn. There's n of those in there, so it's got a basis with n vectors. More than n vectors will be dependent. All right. Now let's go ahead and talk about this next theorem, 4.5.10. If V is a vector space, then every basis is the same size. Okay. We did not prove this first theorem. We are going to prove this one. All right. So whenever you're trying to prove that every type of mathematical object has a property or that some type of mathematical object is unique, often what you can do is sort of suppose there's two and show that they have to be the same. All right, so we're going to say every basis, so let's take two different bases. So we have fancy B1 and fancy B2 be bases of V. And we are going to suppose here that B has m vectors and B2 has n vectors. Okay, so if we want to show that every basis is the same size, what does that mean our goal of this proof is? B1 has size m, B2 has size n. We want to show that they're the same size, so we need to show that m is equal to n. That is our goal. So really, they might be two different bases with different vectors. That's fine, but they're going to have the same number of vectors, the same size. All right. So let's look at a couple of things here. Okay. So B1 is a basis. And let's remember what two properties did a basis have to have? Had to be linearly independent and it had to span V. And then up here, here's a theorem that talks about the size of a basis and dependency of a set. So that's a clue that we might want to use the linear independence here. Okay, so B2 is a basis, or sorry, B1 is a basis, which means that B1 is linearly independent. So it cannot be bigger than B2. Okay, so B1 can't be larger than B2. This is by this previous theorem 4.5.9, because if it was larger, then it would be dependent. Okay, so, oops. if it was larger, it would be linearly dependent, but it can't be linearly dependent because it's a basis, and a basis has to be linearly independent. Okay, so what that tells us is that B1 is not larger than B2, so B1, size of B1 is not larger than size of B2, so we have this relationship here. All right, and then we're going to do a similar thing in the other direction. B2 is a basis, so B2 is linearly independent, okay? So B2 is, put another way, it can't be larger than B1, so it's the same size or smaller than B1, again, by the previous theorem that we talked about. And if B2 is the same size or smaller, then that means that N is less than or equal to M. So now we have this inequality in both directions. The only way for both of these to be true is for them to be equal. Okay, and this proves our theorem. So because we started with just two generic bases, and we showed that any two random generic bases are going to be the same size, that proves our theorem. So every basis is the same size. And we proved our theorem. Great. All right, now that means that no matter what bases we're talking about, they always are the same size. They're always one number in there, right? One number of vectors in that set, which allows us to make the following definition: dimension of a vector space. Okay, and dimension of a vector space is the size of a basis of that vector space. Okay, and by size, we mean the number of vectors. All right, so dimension is size of a basis. Every basis has the same size, so dimension is an invariant. It's always the same. Great. Okay, if V has a finite basis, we say that V is finite dimensional. Okay. Dimension, if we're talking about the vector space containing just 0, dimension of that set we define to be 0. And if V does not have a finite basis, then we call V infinite dimensional. Okay. For us, we are almost exclusively, pretty much exclusively going to be operating here in the finite dimensional world. All right, that is going to be it for this video. That's our definitions and theorems for this section that are pretty important. We'll talk about examples in the next video.